Okay, everybody, welcome back from lunch. We're going to go ahead and get started, keep the program on schedule. Welcome to the session on understanding and addressing noise beyond 65 DNL. I'm Darlene Yapple, your moderator. My fellow co-chair is Callie Grover from Delta Airlines. And also Justin Cook with ESA helped us quite a bit. So she's going to introduce our first speaker.
Hi, I'm Callie Glover with Delta Airlines, and introducing our first speaker, we have Dr. Ameya Behere. Ameya is originally from Mumbai, India. He is a research engineer at the Aerospace Systems Design Lab at Georgia Institute of Technology. His research focus includes modeling and simulation of aviation noise events and the evaluation and optimization of mitigation techniques. He has worked on multiple FAA projects through the Aviation Sustainable Center, ASCENT. In his doctoral dissertation, he investigated the use of advanced computational techniques such as reduced order modeling in the context of aviation noise mitigation. So thank you, Ameya.
Great, thanks, Callie. Looks like I got the enviable spot of first presentation after lunch. I'll try to hold everyone's attention. All right, so I put together the slide deck on some of the research that we're doing at Georgia Tech to improve the accuracy and efficiency of aviation noise modeling. It's not related to any one project. We have a lot of projects under the ASCENT program that Dawn had introduced earlier today. So let's go into it. The motivation slide, this is a little bit redundant for this crowd, but I like to start off my presentations with this. I'll just kind of skip towards the takeaway, which is that we all know that aviation noise is going to be a key barrier to sustainable aviation growth in the future. And a lot of our research is guided by the question of how can we use real-world data and advanced techniques to improve our aviation noise modeling capabilities. So in terms of real-world data, I'm just going to showcase some of the data that we use. So we use a lot of flight trajectory data. We use that for modeling, for validating and improving our noise modeling tools. And we have two different spectrums on there. One is accessibility, how easily it is available. And it's also another one for fidelity. So for example, we have open sky data, which is very easy to access. It's basically open to anyone. But in terms of fidelity, it's pretty low. You would only have like position information on there, maybe some speed. But if you go on to the other end of the spectrum, you would have something like airline FOCA data, which is a lot more parameters. You would have information about the engine state, the flap position, the gear of the aircraft. But of course, unless you work with an airline or get them to give you their data for free, you're not going to have access to any of that. So something in the middle is the threaded track data set. This is a highlight of the latest data set that we have for that for 2021. We have about 3,000 unique airports and 6 million flights. So that's a lot of data that we're working with. On the other side of that, we also have partners for airports, and we use their noise monitoring data as well for our validation efforts. So in the two charts on the bottom there, I'm showcasing how we're using data from the San Francisco airport. You see the arrival and the departure tracks. SFO was one of our first partners for airport noise, but we have since expanded to a lot more different airports as well. So here I've kind of drawn a simplified process of the noise modeling that we kind of go through. Most of you would already know this, but we have to combine data from the aircraft, the airport, as well as ambient weather and such. You feed all of that into an aircraft performance model, which will give you the aircraft trajectory and performance parameters such as speed and thrust. And then you use both of those along with some additional data, put that into a noise model that can do your generation and propagation, and you would end up with a noise metric. Now, if you wanted to do something like a contour, you would have to repeat that tens of thousands of times across all of your receptors, and then you'd need to repeat that for each of the flight. So when I say we're improving the accuracy, we're looking at what inputs go into this process and how we can make that more less error prone. And when I talk about efficiency of the modeling process, we're looking at how we can replace part or all of the process with something that's a lot faster to evaluate. So I'll go into the accuracy part first. We know ADT's APM, the aircraft performance model, is what we took a deep dive into. And we identified three different areas of improvement for departure noise. This is just one of the many projects that we have for improving ADT, but I'm just going to highlight this one here. So we look at the assumptions in these three groups, and we use a lot of real-world data to kind of improve them. So we have improved assumptions for the gross weight of the aircraft, the reduced thrust, as well as NADP 1 and 2 procedures. We've completed the first two. We're still working on the third one. And over the next few slides, I'll go into details as to how we went about these. So in ADT, all of your departures are grouped into something called stage length. So you would have different bins for the trip distance, and you would assign a single weight to all flights within that group. And one of the key assumptions that went into it was a 65% load factor for calculating takeoff gross weight. And I'm sure anyone who flew in here knows that's a very big underprediction, right? So we went ahead and compared how that weight actually looks like in terms of real world data. So in this plot on the bottom left, we see a bunch of blue and orange dots. Each blue dot represents a single OD pair. And what we're showing there is the great circle distance on the x-axis and the gross weight on the y-axis. And the gross weight has been averaged over all the flights that we had data for that specific OD pair. And the orange is indicating what AEDT would assume the gross weight to be. And as you can see, generally, we're under predicting the weight across all of our different OD pairs. So our recommendation to that, which has since been implemented in ADT, is to update all of the weights to be the average of the current and the next stage length. And this has now been implemented in ADT as an AW profile or an alternate weight profile. And this will help reduce some of the underprediction that we might have seen for fuel burn and noise modeling and such. Moving on to takeoff thrust assumptions. Again, the default option in ADT would assume full thrust for takeoff and full climb thrust for the climb. But that's not really what we see in the real world. Unless you're severely performance limited, you wouldn't want to use full thrust for your operations. You can usually do a thrust reduction of up to 15% to save some engine maintenance costs. So we again went into it, and we saw that three additional profiles were recommended for reduced thrust. We're looking at 5, 10, and 15% thrust reduction. And here we can see what the impact of those new options is. So on the top right, we're looking at trajectories, altitude versus ground track distance, full thrust versus the 15% reduced thrust. And as you can see, the trajectory is affected quite a bit. Your reduced thrust will be a lot closer to the ground. But of course, your engine is operating at a lower thrust, so your source noise is lower. So there's definitely competing effects there. And when we actually went ahead and modeled that, what you see on the bottom right is a contour plot comparing the two. And in general, as a rule of thumb, what we saw was that a 1% reduction in thrust would lead to a 1.5% reduction in contour area, of course, up to a point. And again, current ADT version should have these additional modeling options available. What we're currently working on for the APM are noise abatement departure procedures. So the regulations right now are that no more than 2 procedures be developed. Sometimes in a severely constrained case, there might be more than that. But ADT doesn't give you the option of modeling all of those. So if you look at the chart on the bottom right, we have quantified the differences in the DNL noise metric. We're looking at NADP 1 profile versus a standard profile in ADT. And as you can see, it can have quite a bit of difference on the noise contours. And we might see that being implemented in a future ADT version, as it's still currently underway. So pivoting from the accuracy part of it to the efficiency part of it, this part of the presentation isn't really part of any Ascent program. It's more internal research that we're doing at Georgia Tech. And I'm bringing back the flowchart there just to kind of give an idea of what we talked about a few slides ago, wherein you have to repeat the process across multiple receptors and multiple flights. And the reason for that is we're using physics-based or semi-empirical models in ADT, which we have to do to be able to accurately capture your effects of weather and different profiles and the like. But you end up being very computationally expensive because you're repeating that across tens of thousands of points. So the reason this is inefficient is because you treat each receptor point as an independent calculation. That's how ADT does it right now. But of course, we know that's not really independent, right? If we look at the figure on the bottom right, basically I'm showing contours, but I'm showing the receptors instead of the contour lines. And if you pick any point that is in the blue region of that, 80 to 85 SEL, I believe is in this plot, you know that any point that has 4 neighbors that are blue, that point is also going to be blue. It's not going to be like somewhere off the charts. And that's because it's a continuous function across your entire domain of receptor points. So what we're looking at is to use that correlation to our advantage and reduce the number of quantities that you're actually predicting. So this is called model order reduction. Won't go into too much of the technical details there, but we're using this class of reduction techniques to kind of speed up our computation process. So over here, I'm showing some preliminary results from a method called principal component analysis. And there's a lot going on in this plot, so I'll take a second to kind of walk you through what I'm showing here. We see 2 sets of contours. The solid lines are our validation effort, which is from ADT. We're trying to predict that solid lines. The dotted lines is what we ended up predicting. So I would say it's pretty close, but not quite there. And then both these sets of contours are overlaid on a color map in the background. So the color map is referencing the color bar on the right-hand side. Red colors are going to represent over prediction by our tool. Blue is under prediction, and the intensity of the color shows the magnitude of error in that region. So as you can see, contours are mostly coincident from what we obtained. And we have some small pockets of low error. It's about half a decibel here and there. But majority of the region is gray, so that was recreated with 0 error. And the big advantage is that this is a very fast computational technique. We are reducing the number of quantities by almost 1,000. So as you can see, we have real-time predictions for single operations. And the speed itself is impressive, but what's more impressive is what you can do with it. So because it's a lot faster computation, if you have a given amount of time that you have to do something in, you can do a lot more computations and you can evaluate a lot more scenarios. So now you can start thinking about doing something like a true optimization study or parametric trade-off analysis, where, for example, you could take into consideration the local weather at the airport and start optimizing a departure profile for that. And that can keep changing through the day and through the seasons as your weather changes. Of course, there's other things that have to fall into place for that to actually realize, but the modeling part of it is something that can be addressed here. So I want to thank my colleagues and students at Georgia Tech who have helped me with this research, also our FAA sponsors and Ascent collaborators who help us with the resources, and of course our airline and airport partners that help us by giving us data. And I have my email on there if anyone wants to reach out, and I think we're doing questions at the end, so I'll just hand it back to Darlene now. Thank you.
Thank you, Dr. Beher. Our next speakers are going to be Jesse Chancellor and Jim Allardyce. Jesse has served as a resident representative on the BWI Roundtable since inception in 2017, and he's currently the vice chair of the Roundtable's technical committee. Jim is the director and chief consulting officer of Vionair, providing collaborative solutions for impacted communities that provide meaningful, measurable, and implementable results. We're going to be joining their presentation, so we'll start out with Jesse, who is going to be joining us remotely.
I'm happy to be with you, albeit remotely. Today, I'm going to describe how the BWI Community Roundtable developed our virtual airport noise and operations report that uses the number of events above 55 decibels as a key metric. But first, I'll give you some context for the report and some background on the BWI Roundtable. On the screen is a graphic from the report, which isn't available from our airport authority or to our knowledge through the FAA. What it shows are 2 single days of flight paths over our region based on airport operations determined by wind direction. The classic east flow, west flow, some operations are north and south, ours is east and west. It's a good way to see just how saturated much of our region is with air traffic. Next slide, please. I don't think I'm controlling. There we go. And here we can see the problem that was caused by next-gen technologies. The deep red line on the right is post-next-gen. This was all life-altering for many people in our region, as BWI Marshall Airport did not have a large noise population footprint before next-gen was implemented. And that at the bottom, as you can see, is according to our airport authority. Next one, please. Here's another page from our report, which illustrates the post-next-gen noise contours in the Baltimore region generated by monthly operations at BWI. This graphic generates lots of comments in our area because people generally were unaware until we did the report and Van Air did the modeling that significant airport noise pollution at the 55 DNL contour covers an area from east to west that's 22 miles wide and encompasses approximately 125 to 130,000 people. Next slide, please. So, what exactly is the BWI Community Roundtable? Well, we were formed in 2017 after public outrage at NextGen, which was implemented in our airport in 2016. We have 20 voting members and 15 residents chosen by our state senators, 5 members representing county governments and county councils, and there are some non-voting members from industry, the FAA, and our airport authority. It's key to note that we have 3 active committees, one for legislative affairs, one for public communications, and another for technical issues. And our airport is owned by the state of Maryland, unlike a lot of airports around the country, which gives us greater legislative control. Another element of our roundtable is highlighted in green on your screen. In addition to the standard roundtable work on the FAA's Metroplex changes, we crafted our charter more broadly to address environmental effects. And that's how we've been able to create these monthly reports and to support health-related research, which I'll describe in a minute. We're still guided by, at the very bottom, you'll see our first resolution to the FAA in our very first meeting, which was to revert to the dispersion that existed in our area before NextGen, even if that means new, more flexible technologies than the ones that are implemented. All of our decisions are guided by this resolution. We've never taken it back. And in our opinion, it's the only way to restore the balance between the communities and commercial aviation interests that existed pre-NextGen in the Baltimore region. Next slide, please. This next slide is included in our report just because we've been at this for a number of years, and 6 years in total, and we've determined that the interests between the airport and communities are out of whack and unsustainable on the current path. So this is just our standard, we're out of balance slide. Next slide, please. So what have we done in 6 years? The Community Roundtable, we haven't done enough. What we have done is we have an initial set of departure and arrival changes that are slowly, very slowly working their way through the FAA. We started this process in 2017, and we might see implementation in 2025. When, if they're implemented, they'll make some small changes at the margins for some people in our region. And it's interesting to note that this is taking longer than it took the FAA to actually implement NextGen after Congress authorized it in 2012, at least in our region. So it's been a very long process. We also supported, as you see in the second bullet point, a Maryland-funded study by Dr. Zafar Zafari that found that certain health-related costs of NextGen at our airport will cost insurers and individuals over $800 million in over 30 years in today's money. And that's an incremental number in Dr. Zafari's study above the cost of simply having the airport, even without NextGen, which we calculate to be close to another $800 million in present value. So it's a costly public health thing to have the airport just in general. And most recently, we sponsored successful legislation to reform our governing body of the airport authority by adding community members, expanding the charter to explicitly consider community health and in the environment when making decisions at the airport. And the governor's waiting. And lastly, we worked with Van Air Incorporated, Air to create the monthly report, which we'll start describing. We didn't really want to create these reports, but we found that we had no choice because we found that the FAA nor the MAA planned to do any pre and post implementation analysis of the flight path changes we were negotiating. So then we started looking for regional wide comprehensive noise data covering all the overflown communities. And we were again surprised that the airport has very limited data and there were no other comprehensive data sets. And from most of our prior lives, we couldn't understand how decisions affecting tens of thousands of people had no real world analysis after implementation. So we created our own with the help of Jim Allardyce and his team at Air. And our first decision, which you see at the last bullet point, was to go beyond DNL in order to have any public credibility and to be understood, because DNL is not understood. So we had to come up with a different metric. Next slide, please. So in working with, sorry about this. Yeah. So in working with Van Air, we agreed the N above is both more understandable and a better metric to reflect what people are experiencing. It really is what people get. It reflects how next gen changed their lives. But we also use DNL because that's still how the FAA makes decisions. So we have to use both in order to be able to make apples to apples comparisons with their analysis. And the last point on this page is that we also initiated the report to keep a comprehensive record of operations and pollution to aid in future public health research. Jim's going to cover the key elements of our reports in his slide. So I'll only emphasize the first 3 points here. We go beyond the 65 DNL, which is pretty small and pretty meaningless. So our contours are drawn out to 40 DNL. And it's important to know that in our report, we identify specific landmarks that are recognizable to the residents, such as schools and parks and hospitals, where noise pollution is being captured. And so with that, I'll turn it over to Jim, who will go over the monthly report in more detail.
So I get the kind of nuts and bolts piece of this and kind of how we did it. Jesse kind of told you what and why. But what we do, generally speaking, is work directly with the communities. And one of the things that we did here was worked with the actual roundtable. We were actually hired by the 2 counties, and we worked with people that were represented on the roundtable to see if we could find a way to present all this cool data that you have been seeing here in a more understandable manner to the community at large. So we want to make sure that we understand their concerns, their priorities, and be able to communicate the impacts that we see through the data in a manner that uses common language and ensures a mutual understanding between all parties. And when I say all parties, I mean not just the folks in the community, but the airport and the FAA. So we're all singing from the same sheet of music. We also want to acknowledge that the impact to communities outside of the 65 DNL is real. And the number above metric that we decided we're going to use in this allows people to see that there are impacts sometimes, 75 DNL or 75 decibels and above in an instantaneous reading that happen to these people that are outside the 65 DNL. So there is impact to them that probably isn't fully captured with the DNL metric. And next slide. So BWI Airport, kind of located right in the middle between the two counties that we worked with. Anne Arundel is kind of to the south and east, and Howard is kind of to the west and north. And the airspace and flight procedures that Jesse talked about, have been pending for quite a while. But what we wanted to try to do was establish a baseline so that when the new procedures are implemented, we have a basis of comparison to see exactly what the impacts are, positive or negative, of the new procedures once they get implemented. How do we do that? These are the data sets that we usually look at. We get predominant flight paths. One of the things that top left slide shows a contouring of, it's not really a contour, but it's a heat map of where the most dense tracks are. We have runway use, fleet mix, total operations, daily operations, daytime versus nighttime, and we do passenger versus cargo operations in this specific report that we're doing for the folks up there in Howard County and Anne Arundel County. We also do day-night level, the DNL contours. We have a county grid that we also put in there. That's kind of the bottom picture. One of the things that we can do is just draw a grid of virtual noise monitors, and that's what these are. They're virtual noise monitors, and they can be laid out up to 1,000 monitors, and the density depends on how much of an area that you're trying to cover. But we had a pretty good density throughout both the counties. And we can also use specific landmark locations. In other words, if there's a school or a church or just an area of interest that you particularly want to know, we can just drop a noise monitor right on that. So we're not limited by the physical noise monitors and their placements with real estate and all that stuff you have to worry about to get those things out there. And then we also take all that data from these monitors. We also present it in both graphic and tabular forms. And number above 55 in the county grid and the landmark locations is in tabular and graphic is one of the things that they had requested us to provide for them. And you go to the next slide, we can show you some of the things. So for those of you that are like really smart people and like tables and data and all that kind of stuff, we got that. Okay. For those of you who are more like me that like to see pictures, we do pretty pictures. So the one on the right basically is what it shows at each monitor location. It shows you the number of times that the noise and instantaneous noise exceeded a particular level. And this one, it happens to be a number above 55. But we do 55, 65, 70, we can do anything. But we've settled 55, 65, 75 normally. And in some places that are close to the airports, we do some number above 85. And then we give you a little bit of an idea of day versus nighttime operations in that chart to the bottom left. So you can see on a daily basis where the major operations are. We can break it down into kind of any category that you want as far as aircraft types, engine types, whatever, and it's customizable. So we have worked with the community up there in around BWI to try to get the metrics and the graphics and the report in such a fashion that it is most easily digestible by the layperson. And so these are some of the metrics that we've used, and we can further customize it as things goes on. We've actually done that quite a bit over the time. As we would present a report and they say it would be really cool if you could do this. So we continue to customize as we go. So I think that's it. Next slide, and that's back to Jesse.
We're a little over time right now, so I just want to draw your attention very quickly to two points from one of the earlier slides that Jim gave you. This is for the landmarks in Howard County. And if you look at the top location, it's a high school that has 189 daily flights above 5 decibels. And it's at a DNL of 58. If you look at the lower one, it has 12 average daily flights above 55 decibels. But the DNL is just barely over 40. So given the fact that there would be over 68,000 flights annually over the first location and very few, relatively speaking, over the second, it just shows the DNL doesn't actually capture what's happening in our community. And in fact, in general, it's just not an accurate measure or metric. Next slide, please, and then we'll wrap this up. So there are a lot of points here. It's a lot of data, so I'm just going to focus on a couple. The first one, in above for us is best for conveying the severity of noise pollution because people understand it. It shows what happens. The third report is we're trying to bring stakeholders together to negotiate at our airport over operations and future infrastructure, but we need a common set of facts. And so we think our report is that common set of facts, at least we hope so. But the fourth bullet point says that we're not naive. We know that there are very few incentives for the aviation industry to treat communities as stakeholders. So we're trying to work with them, and ultimately we think we'll have to keep pushing hard on the political and airport governance fronts to recreate the balance in our community. And I guess for us, the risk of failure is that we lose support politically in our region for airport growth, which is already starting to happen. So we really need to get a set of facts that we all agree on to start. That's it. Thank you.
Okay, thank you, Jesse and Jim. And our next speaker is Dr. Cindy Christensen. She is the co-founder of Aviation Impacted Communities Alliance, AICA, and Boston Fair Skies. She previously served as a member of the Massport and the Logan Community Advisory Committees. She is a biostatistics course director at Boston University of Dental Medicine, is a health policy researcher with a PhD in statistics, teaching statistics to graduate students, and is a fellow of the American Statistical Association. Welcome, Cindy.
Thanks, Diane. If you can't hear me, please let me know. The worst thing that can happen during a presentation is to not be able to hear the speaker. I'm dedicating my presentation to my colleague and friend, Carl Morris, who died last week. Carl was had a degree from Caltech in 1960 in aeronautical engineering. He smartly, in my opinion, turned into a statistician with his PhD from Stanford. So the title of my talk is asking the question, is it time to retire a 30-year-old metric? I'll start off with problems with the FAA's DNL 65 noise policy. I'll focus on FAA noise policy and ASNA, next-gen procedures, how changes were made to flight paths, but no significant change to noise policy. And then also I want to talk in a statistical sense, how DNL 65 is an invalid metric for locations far from the airport. Starting with ASNA, ASNA requires the FAA to establish a single system of measuring noise that's based on surveyed reactions of people to noise. Again, the second element of that was focused on a single system. In their 2018 report to Congress, the FAA concluded that no single metric can cover all situations due to the dynamic, acoustical, and operation characteristics of aviation noise. Yet, the FAA does not use the required single system. It uses the single noise metric DNL 65. As you know, the FAA also misinterprets ASNA when they state in their neighborhood environmental study report, they say Congress directed the FAA to establish a single metric. As you saw, that's false. It's a single system. In their 2018 report, the FAA uses this table to summarize its noise metric information The Aviation Impacted Communities, in its technical report to the Congressional Quiet Skies Caucus, corrected the table. For example, when the FAA reports that DNL accounts for the number of events, when you average over the number of events, that's not accounting for it. They may use it in the calculations, but it's not accounting for it. Also, the information under and above, I believe, was incorrectly specified. They claimed in the table that the time of day is not included, which of course is correct, but there's always easy ways of penalizing for time of day or other reasons that should be penalized, just as they do with the DNL metric. You've all seen slides like this. This is showing how NextGen affected departures at the Boston area. No change made to the significant noise definition. Again, it's away from the airport that things are now different. This is another example of how NextGen has affected away from the airport locations. This the chart on the right shows 6 large jet arrivals to Boston in just 7 minutes. So with the FAA's attempt to increase capacity, it's decreased the time between noise events, which is an effect for locations away from the airport. You've seen this slide before. The FAA likes to use this graphic to show a steep decline in noise. At the same time, there's been a steep increase in number of passengers. However, the noise exposure trend is misleading because they're using the outdated DNL 65. The trend covers 45 years. And I use this in my statistics class to show an example of I'll say the book, How to Lie with Statistics. Because if you look at just the last 10 years, the upward trend in number exposed since 2010 has been a 39% increase. Now I'd like to talk about why DNL 65 is an invalid metric. In statistics, a measurement system is valid if it measures what it claims to measure. So in this case, significant noise. And the results closely correspond to real world values. So in other words, survey reactions of people to noise. In statistics, a measurement system is valid if it's both accurate and precise. We also use the terms unbiased with small error or variability. This is an example of how you might experience noise if you live away from the airport in a 90-second time period. 2 airplanes, both being heard for 24 seconds, 42 seconds in between, ambient noise level of 50 dB. The DNL is calculated as if the people actually heard not 48 seconds, but 2 seconds of noise at slightly higher dB. So this is what we say does not capture the experience and causes DNL 65 to be an invalid metric for noise sensitivity. You've seen this before too. This actually is something that I looked at when I was trying to figure out in some neighborhoods, can they ever reach significant noise? And once I figured out no, I thought that I must have made a mathematical mistake. I did not. For people away from the airport, there's no way that most people could ever get significant noise. This causes me to wonder why we even do environmental assessments that look at areas 5 or more miles from the airport. I also question the current NEPA's requirements for reportable noise to be 3 decibels or 5 decibels increases, when that would mean a doubling of noise or a tripling of noise, which just is not going to happen even with the concentrated flight paths. Here's another reason why the DNL 65 metric is invalid for those away from the airport. According to Vince Mestry from 2 years ago at this exact symposium, I asked the question, what's the margin of error? That's the statisticians like to know that. For these DNL estimates, he responded that at 65, it's gotten pretty good, 1.5 decibels. But when you get out to the 50, an estimate of 50 DNL, it could be as plus or minus 10. So what you see in the graphic below, the first line in green is DNL 50. So assume that your area has an estimated DNL of 50. According to Vince, that number in reality with 95% confidence could be as low as 40 or as high as 60. That causes DNL 65 to be an invalid metric as far as statisticians are concerned, including me. Here's the Schultz curve versus the National Environmental Survey. This is another reason that the DNL 65 threshold is invalid. You've seen this before, so I won't go over it, but just a few points about what makes the NES curve different. The Schultz curve looked at all transportation noise. The NES curve was a specific study designed to capture annoyance to aviation noise. It included US data from residents living in 20 airports. The Schultz curve used international data. The NES folks who analyzed this, you could use the state-of-the-art statistical modeling, whereas the Schultz curve used inappropriate statistical modeling, although they did the best they could at the time they were able to develop it. And also importantly, as far as assessing whether or not it's a valid metric, the NES curve is closer to what communities report as significant noise. So let's talk about solutions. Two main topics here. One is to separate mitigation efforts close to the airport from those away from the airport. The second is how to develop a valid system of metrics to define significant noise for those two situations. So the FAA uses the single metric DNL 65 for these reasons: residential land use compatibility, second, eligibility for noise mitigation funding, and then also for NEPA, as you know. The FAA also says, though, in its policies and procedures implementing NEPA, the FAA has exercised its discretion. So it's not mandatory that all of those three use the same system of metrics. I believe that the FAA noise policy must separate number 2, eligibility for noise mitigation, from number 3, NEPA requirements for its regulatory purposes. How to create a valid system of metrics to assess noise: take public comments, complaints, and create metrics that capture the cause of the complaint. This cannot be done by a computer model. For example, someone complains there's too many planes. Think about using N above. Someone complains about almost constant noise. Think about N above per hour. Someone says it wakes me up every day before 5 a.m. Think about using N above with penalties for early morning noise. Someone says without planes, I live in a quiet community. Think about accounting for ambient noise in the system of metrics. I believe the FAA needs a multidisciplinary team in its regulatory decision-making process. I believe it should contract with the National Academies of Medicine so that it has the expertise it needs to understand how its policy affects quality of life and health of the people underneath these paths and away from the airport. They should include environmental health, statistical, measurement theory, medical, public health, sleep psychology, and a bunch of other experts. So, what should a noise metric system include for regulatory purposes? Include something that captures variation in noise. This is a graphic I use in my class. If you have your head in the freezer, your feet in the fire, on average, you're just fine. But we need something that captures variation. This next one, I'm not going to read out loud, but you can read it. This is basically what DNL is. It's a single metric that uses log 10, an average of the sound pressure level across 86,400 seconds. Nobody understands that. The third bullet point. Do use and above for away from airport locations, the number of noise events, especially under NextGen Pass. That's what affects residents' health and quality of life, even though the sound intensity is lower than close to the airport. Also, it's easy to count. We learn how to do that when we're 3 years old. And we understand counts. It's also easy to understand when too much is too much. Don't include metrics that do include metrics that do not correlate well with DNL. This is from 2011, where Mestry et al. Wrote in a report to the FAA. This approach can help to determine whether noise metrics other than DNL could yield meaningful different predictions of noise exposure for a typical airport, and hence support predictions of noise impacts potentially different than those produced by DNL. So if you haven't seen that report lately, look it up. And as part of the noise policy, we need a system that does not, of metrics, some of which do not correlate well with DNL. Final slide, count the number of aviation noise events. I believe that the FAA can do this and do this quickly before the comment period is over. Talking about the neighborhood environmental study, they included other metrics in their analysis, like and above. They included whether or not you could see the airplane, things like that. But focusing on and above, I believe that with the data that the FAA has, it could do a better analysis of the and above data. All that they did in the survey analysis was to interact and above with DNL. So we do not know from this study whether or not and above is as good of a predictor as the people on the ground are telling us it would be. All you have to do in the model is get rid of those two terms and do just as they did with DNL, have an independent predictor of and above. I believe that the FAA could do this with 1 day of programmer's time and 1 more day of writing up the results. And this is something that should be done immediately. Thank you.
Let's do the first question for Dr. Behar. Is the model order reduction process that you at Georgia Tech have developed mature enough to be implemented within AEDT or as a supplemental script?
I wish I could say it was mature enough, but it's not close. What we've done so far is just an exploration of the model, and we see good results. But again, it's only one aircraft type. We've not looked at different weather conditions yet. So I think it is promising, but it's not mature enough right now. Probably a supplemental script would be a good idea. If anyone wants any more details, I could email you a few papers that we've written about it.
Okay, Vioneer, what is the correlation between and above and DNL? Based on your table, some areas were negatively correlated.
You want to answer that, Starbucks?
Maybe we could get him a mic.
Got
Hang
it.
on a second.
Thank you.
So can you repeat what is the correlation between DNL and
DNL and above.
so if it's very close to the airport, they seem to be correlated, but then the further out you go, there's not really any information from DNL like we heard in the last presentation.
Okay. Cindy, what should be the threshold for and above?
I have a suggestion, and if you're familiar with the MIT Massport study, Dr. Hansman used a threshold of a decibel threshold of 60 during the day, 50 at night, and he looked at peak day where there were 50 or more events. So that's a place to start. As I mentioned, the NES data has loads of information that will help us with that decision. But for right now, I would say 60 during the day, 50 at night, count those events. And if there's more than 50, you say that these people have significant noise.
Dr. Bahir, what is the source of all the flight data that you analyze, and would it be possible to get reverse flow flights to account for areas adjacent to airports?
So I'll answer the first part. The source of the data is, a lot of it is open source for OpenSky, for example, is from ADSB, so anyone can access it. The FOCA data is from our airline partner, so it's mostly similar to flight data recorder. It's all onboard sensors from the aircraft. Yeah, for the reverse flow, I think usually we try to model all the flights that we have corresponding noise monitor data for. And it so happens that sometimes for locations like SFO, if you have the ground tracks going over the city, the noise monitor data isn't, it has low reliability in being linked to that particular flight. So our SFO noise monitor partner, they tell us the confidence that they have that a specific recording can be associated to that flight. And we only deal with class 1 recordings, which is the highest level of confidence. So I think that might have ruled out some of the reverse flow, but we can definitely consider it if we have the reliable data for that.
Questions for Jesse? Since the FAA didn't want to do delayed assessment of your requests some period after the implementation, who have you contacted in Congress?
Yeah, we've been very active with our congressional delegation here in Maryland, and we've also worked with other roundtables with Quiet Skies Coalition in Congress, the caucus. And, quite frankly, we believe that the FAA simply is not going to do that work. We don't think it's going to happen in time for us to capture the pre and post, because the pre is happening now. And so we basically decided that the FAA is not going to be a partner in that. And if our congressional delegations make some headway, either through the FAA appropriations or through other means, that would be great. But we've given up on that process with them.
Jim, why did you select and above 55? Is there a technical reason for that decision where non-aircraft noise events accounted for?
Of all the metrics that are available for use, it seems just to be the one that the communities identify with the most and the best and the easiest. We've used it in several different locations, and some of the other metrics are still a little bit confusing. This one is pretty much straightforward. It's the maximum noise you hear instantaneously and how many times you heard that at that location. It's just very straightforward and people can relate. And so that's just why we do it. Yeah.
Thank you. Cindy, what metric effectively represents noise exposure in communities 5 and higher miles away from the airport?
I believe that that's and above. This is what I hear from the people that I work with, both locally and at the national level. They all say it's the number of planes that are flying over us. I mean, they also mentioned they're waking me up, things like that, but I believe and above can be used with penalties, just like they do with DNL. And, it doesn't have to just be a nighttime penalty. There could be a penalty for every plane that flies over the same location more than 50 times in, say, a 8-hour period, something like that. So there are a lot of ways of using and above and helping it actually represent what people are experiencing.
Dr. Bahir, any improvements on arrivals noise modeling?
Right. Yeah, that's a good question. I kind of just only focus on the departure part of things in the presentation. For arrivals, what we found is having the airframe noise included is a big part of it, and accounting for configuration of the aircraft in the NPD is very important. So ADT right now only has one NPD, and that's manufacturer provided. The easiest solution would be to just ask manufacturers for additional NPDs for each configuration, but there's some very severe backlash or resistance to including that from what we've seen. So what we're trying to do at Georgia Tech, and I didn't have it on the slides, but we're trying to come up with a correction function that can account for different configurations. And we would just correct the NPD and then use that depending on the phase of flight. But it's still in the research phase, so I didn't have any results for that today.
And this is to Jesse and Jim. How do you account for altitude, distance of aircraft from with and above in relationship to DNL?
Well, everything that we use is based on flight track data. We use swim data to get the location, altitude, everything of the aircraft. The model also includes temperature, pressure variations, all that stuff. So it's been validated, very accurate with actual physical noise monitors. And so you also, if you're saying altitude, if you're also talking about terrain, that's also included in the model. In other words, we know the MSL height of the virtual noise monitor, wherever they place that, and then you can calculate the AGL height of the aircraft, and then you can correlate that with the noise that you're experiencing.
Cindy, what are your thoughts on how recommended metrics should relate to the WHO community guidelines for aviation noise, 45 day, 40 night?
Well, as most of you know, the WHO thresholds are lower, so that's good. However, they still use DNL, so that's not so good. But I want to say, because I kind of like this example of what we need. We need a National Academy's Division of Medicine ruling consensus report on this. When I first started working on this back in 2015, I was told by my congressional representative that Congress needs things that are, and he said with air quotes, American made. So although we've got all the information we need from WHO, his response to me was that that's not going to help change policy. So how can we change policy? Use the National Academy's Division of Medicine, which is set up to be an independent organization from the federal government and that offers consensus reports from true experts from across the country, thus making it American made.
Okay, I think this will be the last question. Jesse and Jim, were there any benefits to the BWI path changes? Are there options that don't just overfly other residential areas, including the status quo?
I'll let Jesse answer that.
Jesse?
Answer that.
Yeah, I'll answer that. We looked at every possible path using RNAV technology. And I think some of the people who helped us do that analysis are probably in the room there. You know, it's a very inflexible technology. As long as we have that technology, there will be a lot of noise and a lot of people will feel the pain of it. So what we did is we chose the path that had the most benefit to the greatest number of people. And as I said earlier, it will make some improvements for some people slightly at the margins of the problem, but it is not a comprehensive solution. Flight path changes help, but they are not the solution.
Okay, this concludes our session. A special thank you to our knowledgeable panelists, our engaged audience, and our co-organizers, Callie and Justin. Thank you very much for having a break.